Executives sit in corporate boardrooms looking at dashboards displaying world-class 85% machine utilization rates. They feel successful. Meanwhile, out on the physical factory floor, their shipping docks remain inexplicably empty. This disconnect is a byproduct of the metric used to track it, overall equipment effectiveness, or OEE. It combines availability, performance, and quality. An 85% score is mathematically world-class, but as a physical measurement, it is often false. The leak hides in the performance category. It is driven by idling and minor stops, events industrial engineers call micro-downtimes. A material jam or a sensor trip takes just 4 minutes to clear. But if an operator clears an unrecorded jam 18 times during a shift, it removes exactly 72 minutes of production capacity. Because these stops are brief, relying on human operators to track them ensures they go unrecorded. The result is a multi-million-dollar mathematical lie at the executive level. Consider the floor operator's reality. Clearing a minor material jam or resetting a sensor takes between 40 seconds and 2 minutes of manual labor. Operators are paid to keep the line moving, not to act as data entry clerks. To maintain throughput, they fix the physical issue and immediately return to production, which means they skip the manual log entirely. These 72 minutes represent 15% of a standard 8-hour shift. Multiplied across a year, this invisible friction accounts for thousands of hours of lost production time. Demanding that a workforce log 30-second jams is a structural failure of management. It expects humans to act like telemetry systems. To reclaim this lost time, manufacturing leaders must separate human labor from machine data by relying on objective hardware. The 6 Big Losses framework maps lost production to availability, performance, and quality. Availability losses trigger alarms and are logged. Quality losses are tracked via part counts. That leaves performance, specifically idling and minor stops. This anomaly is underestimated because it leaves no paper trail. These stops are caused by mundane physical failures, a proximity sensor obscured by metallic dust, or a misaligned feeder that requires a manual nudge every 12 minutes. Because a minor stop doesn't require a repair team, it requires a different diagnostic approach than a broken motor. You cannot fix what you cannot see. Since these events are invisible to management, they require a localized hardware intervention to detect, rather than a human policy change. The hardware mandate is to tap into the raw physics of the machine. You eliminate manual logs by measuring electricity instead of human activity. A basic clamp-on current sensor is wired directly from the machine's drive motor to the programmable logic controller. We define downtime by electrical load. If the drive motor is not drawing operational currents, the machine is down, regardless of operator logs. The controller receives this analog voltage drop and translates the physical state into a digital signal. This state data is pushed to an edge gateway, a specialized computing node positioned on the factory floor. The gateway runs a script to filter the noise, logging the exact timestamp of any load drop lasting longer than 30 seconds. The final step is pushing these objective, flat text files to a cloud database without any human interaction. Hardware sensors do not negotiate or forget. They simply transmit the objective electrical truth of the asset. Once the architecture is proven on a single bottleneck, it can be scaled across the entire production line. This data feeds a digital twin, a centralized model of the entire manufacturing process. Engineers correlate machine stops with specific workflow intervals. If the data shows a machine stalls every time a pallet is replaced, the digital twin identifies a material handling bottleneck. Identifying the bottleneck allows the team to move from digital modeling back to the physical floor with a specific target. Instead of hiring more labor, engineers can deploy modular, passive automation. If the data showed a stop caused by empty parts bins, they can implement karakuri mechanisms to keep materials flowing mechanically. This cycle transforms maintenance from a reactive emergency response into a planned engineering iteration. The digital twin exists solely to execute these targeted physical redesigns. Data without physical modification is just overhead. New tracking sensors often face cultural resistance. Operators may view them as a punitive tool designed to monitor their individual speed or bathroom breaks. Leadership must reframe the technology. Operators are skilled builders, and automated telemetry removes the administrative burden of being a data entry clerk. The goal is to diagnose the engineering process, not the person. When the machine reports its own state, the operator is free to focus on production. With the workforce on board, leadership can take this objective architecture to the board for financial validation. The ROI is concrete. Reclaiming 72 minutes of lost production per shift across 3 shifts creates hundreds of additional hours of machine availability every year. By multiplying that reclaimed time by the machine's hourly throughput, a company can see millions of dollars in annual revenue gains without buying a single new machine. Securing workforce trust and unlocking these financial returns both rely on establishing an objective hardware baseline. Removing manual logging requirements clarifies the operator's daily function. It is the industrial design rule of form follows function, applied to management. The operator's function is to produce. The sensor's function is to record. This crucial shift eliminates subjective, human-biased machine data from corporate reporting entirely. The era of dashboard illusions ends, and the era of the transparent factory begins. Achieving truth on the factory floor is a physics and engineering challenge. It was never a personnel management problem. Recall the paradox: a green dashboard and an empty shipping dock. By eliminating the 72-minute micro-downtime drain, the digital metrics finally align with the physical output. The dock actually fills. This fundamental shift allows corporate executives to transition from managing reactive daily chaos to directing proactive, predictive engineering. This process brings the hidden capacity of the factory into the light, reclaiming 15% of every shift. Executives who continue to rely on manual entry to measure machine physics will remain blind to their most expensive corporate bottlenecks.